Good morning from New York City. It's sweltering these days. We're in the middle of a heat wave. I just got back from Nantucket where I got some sea and fresh air, and now back into the city, which is kind of muggy. I think I want to go back up there. Anyway, I'll tell you where we came from and where we're going with this series of lectures. This series of lectures is basically college physics. I'm actually beginning with electromagnetism. Usually it's traditional to start off with classical mechanics. I've actually done a lot of classical mechanics in another on another channel, Dermot O'Reilly channel, and I didn't want to just repeat myself again. I may include classical mechanics and thermodynamics after doing electromagnetism. So basically I'm going to do electromagnetism, and I will give you an outline of what we're going to do. We're going to do the electric field, we're going to do the magnetic field, we're going to do electromagnetic waves and radiation. We may finish up with a bit of special relativity, haven't decided that yet. One way or another, it's everything to do with electricity and magnetism. I'm also going to do a little piece of history, the history of electricity and magnetism. So, but first of all, I'm beginning with preliminary mathematical methods. So, I started off with the scientific method, just a rudimentary introduction. It's traditional in colleges to use that notation, but I actually didn't just introduce it, I showed you how to manipulate such expressions, because calculations finally come down to putting in numbers, usually in scientific notation, and finding a result. Now the next lecture I gave, lecture number 2, this is lecture number 3. Lecture number 2 covered units, SI units particularly, but also conversions using the unit factor. Now this one, I'm going to have a quick look at dimensional analysis. And the next lecture, I will start going into vectors, right? Actually, no, I may put in an example of a dimensional analysis, a big problem, actually finding the Planck length. I've actually done it before, but I'm going to include it in this particular group of lectures, just so that you can see the sequence and you can, instead of having a playlist, just go through the whole channel. Then after that, I'll launch into, after I finish vectors, I'll do a little bit of the history of electricity, going back to Gilbert, who is like, and before Gilbert, the Greeks. And then I'll launch into the electric field and all the basic electricity stuff itself. So, dimensional consistency. Let's talk about dimensional analysis. Now, if you Google dimensional analysis, you get a heap of garbage coming up. You have to really look for proper dimensional analysis. What they start talking about is they start talking about unit conversions. That's not dimensional analysis at all. If you Google it, that's all you get. So follow this. There are some good sites on dimensional analysis, but they're hard to find. So what does that mean? Well, physical quantities may be dimensionless or dimensional full. For example, let's look at these. Length has the dimension of length. Length squared. Area has the dimension of length squared or square meters. That's in units. These are the units, this is the dimensionality. We're actually going to use the units because it's easier to write. Length cubed, the dimension of volume, meters cubed. Time, the dimension of time, time to the 1, seconds. Length over time, meters over seconds. What's that going to be? Meters over seconds, speed. Length over second squared, meters over second squared. Length over, this should be length here, yeah. Acceleration, the dimensions of acceleration. Meters per second. What's this one? Oh, it's going to be, this is going to be force, length, no, times meters over second squared. Kilograms meters of a second squared, yeah, it's force. And this would be energy, I guess. No, pressure, I put it down here. All right, this is going to be an exercise which I'll tell you about at the end. I'll explain that in a minute. The general idea is this. Suppose we have two physical quantities, A with dimensionality like this, and B with dimensionality like this, and we want to end up in an expression which is of dimension length only. Meters to the power of 1, kilograms to the power of 0, seconds to the power of 0. This is going to be 1, and we're going to end up with something of dimension length to the power of 1. So we put in the various quantities. Let's say kilograms to the power of x1 is the dimensionality of A in terms of mass. Meters to the power of x2, the dimensionality in terms of length for A. And seconds to the power of x3, the dimensionality of A in terms of time. In other words, that would be mass to the power of x1 in traditional notation, but we're not using that notation. Now B has a similar setup, but we'll give the variables x4, x5 and x6 to the dimensionality of B in terms of mass, length and time. And we need to end up with this. Now let's look at kilograms first. Well, kilograms are going to be of dimension 0 on the right hand side. So we go x1 to the power of, actually there's an A here, we need to find out what A here is, and B, let's say. So, x1 to the power of A times x1 to the power of B is going to be an equation which is 0. We find out, we write down the result for that. Now similarly here, x2 to the power of A, x5 to the power of B gives us that equation. And similarly we could have one for the other ones, these ones. Third equation, right? And you should end up with the same number of equations as unknowns, and then you solve. Now I've got an example whereby I do this, and I'm posting it in the next class. It's an example, and it's about as much as you can get in dimensional analysis. I keep tending to say dimensional regularization, but that's not what I mean. Let's do a quick example. So we know that the period of a simple pendulum is given by 2 pi root L over G. Let's check if that equation is dimensionally correct. So we'll square the time. T squared is dimension of time squared, or second squared. 2 pi is dimensionless, so we need not include that in our result. When we square the square root of L over G, I get L over G. We get rid of the square root. Now, L has dimension of length, and G has dimensions of meters over second squared. And 1 over A over B is B over A. So we get dimensions of time squared, or second squared. So the equation T equals 2 pi root L over G is dimensionally correct. Okay? So I'll let you study that, take a screenshot of it, and then I'll give you your exercise. Your exercise to go home and check is the following. So, what are we going to do? Give you an exercise. I'll give you 2. Because that general equation makes things look a little bit too complicated. Now, dimensional analysis is much more useful in fluid dynamics than anything else, but we can use it in all aspects of physics. So at home, what you can do is the following. Now I can't remember if it's K over M, but it could be M over K. Go and check. Check if it's K over M or M over K, I can't remember. Do the same thing for that, just the same way as I did this. the next one is to show that that is dimensionless. Coulomb squared, Newton meter squared. Show that this object is dimensionless. You say, well, what about the e squared up here? That's going to have dimensions of Coulomb squared. You'll see that it's going to be cancelled due to the dimensionality of the permittivity of free space. So that's your exercise. Go away and duplicate that. Now, a more advanced example in dimensional analysis would be the following. Try to find the Planck mass. Make an expression for it. It's going to be some function of G, H cross, and C. Find out what the function of G, H cross, and C is, and I'll give you a clue. The clue is, watch the next lecture where I find the Planck length. Okay? Now here on in we're going to move in with more mathematical methods which go beyond what we need for electricity. But in electricity we do need a couple of things. We need to be able to add and subtract vectors, and we need to be able to work with the scalar product and the cross product. So I'm going to do the cross product just as Survey and Jewett level, but I'll also go to a much more advanced level with the cross product just for fun, using the epsilons, and I'll post those. It'll be 3 classes in vectors coming up. You don't need all of them. You really need only the first one, or maybe the first and the second. You can skip the third one. It's optional. So vectors is coming up. Then after that we'll go into the history of electricity, and we'll then move into the actual, lectures on electric field and magnetic field, and it'll get more nuts and boltsy. But all this stuff is important, and the vectors class I give will also be necessary for classical mechanics. They will not be necessary for thermodynamics, because thermodynamics doesn't really involve the use of vectors. Now, vectors are mathematical devices. Some people say things like this: force is a vector. Force is not a vector. Force is a physical quantity that can be represented by a vector. And what's a vector? A vector is a device that keeps track of components. That's all. Let's get rid of this on the board, and I'll show you what's coming up. It just so happens that certain physical quantities can be resolved into components. And those physical quantities can be listed quite quickly, because fundamentally there are several things in physics. Mathematical devices used in physics to represent physical quantities are like this. First of all, scalars. Scalars are just numbers. Mass, length, and time can be represented just by numbers. So can temperature and electric charge. Okay? All right. Power. Just a number. It's not going anywhere. Now, physical quantities that can be represented by resolved into components and be represented by vectors would be, for example, displacement, velocity, acceleration, force, angular momentum, torque, and that's about it, right? Let's see what we mean by a vector anyway. Suppose we have a bag of fruit. And in it we have 3 apples, 2 pears, and 4 lemons. Okay? Now sometimes people put vectors like this. They're unit vectors, and they have scalars multiplying them. Okay, so that's one convention, but you can also represent it by slots, so long as you understand that the first slot represents apples, the second slot represents pears, and the third slot represents lemons. And we take another vector v2. Now the second bag only has no apples, 4 pears, and 1 lemon. But if I take the resultant for the 2 bags, if I throw the 2 bags together, I get 3 plus 0 is 3 apples, 4 plus 2 is 6 pears, and 4 and 1 is 5 lemons, or simply the new vector R. Okay? The new vector is the resultant of adding the 2. That's fundamentally the way vectors work, but slightly, in reality, vectors have a slightly different, when they're represented in orthogonal frames of reference and stuff like that, it gets a little bit more complicated. This is a very beginning notion of a vector. Okay, let's wrap that one up and say that's where we're going. See you again soon for the next lecture.